Welcome back to Discrete Mathematics. Today we're going to take a look at recurrence relations. So what is a recurrence relation? A recurrence relation occurs when some number in a sequence depends on the previous numbers. So a good example is the Fibonacci sequence. So we start off with the numbers 0 and 1, and then the next number in the sequence is always going to be the previous two added together. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, so on and so forth. So that's the counting sequence. More formally, we can define the nth number, an, to be equal to the sum of the two previous numbers. So we can say this is an minus 1 plus an minus 2. Commonly, you'll see this with Fibonacci written fn is equal to fn minus 1 plus fn minus 2. I'm just going to use a's to be consistent with all of my examples. So this is for n greater or equal to 2 because we don't want a of negative 2 because we can't have the negative 2th number in a sequence. Doesn't make any sense. So we have an is equal to an minus 1 plus an minus 2. The problem is right now is that n has to be greater than or equal to 2. So a2 is equal to a1 plus a0, but I haven't defined what a1 and a0 are yet. We need those two. So we'll start off the sequence by saying that a0 is equal to 0 and a1 is equal to 1. And that is the formal definition of the Fibonacci sequence. So let's take a look at another type of sequence, a geometric progression. Okay, so 3, 6, 12, 24, 48. Okay, this seems pretty straightforward. Let's write out a formal definition for this. Okay, an is equal to, okay, if we take some nth number, some arbitrary number, in fact, let's take 48. How do we get 48? Well, we take the previous number, an minus 1, and then we multiply it by 2. And of course, this has to be for n greater or equal to 1, because we need one previous number to figure out what the current number is. And what is the first number in the sequence to start it off? Well, that's the number 3. So this is the recurrence relation for this sequence. Now what's nice about this is that we can figure out a5, a8, a12, we can figure out whatever we want. The only problem is when I say, hey, what's a of 667? Well, that's going to be 2 times a of 666, but hold on a second, what's a of 666? Well, we just need to figure out that a of 666 is just 2 times a of 550 or 665. Okay, so if you know a of 665, then you can figure out a666 and a667. But that's kind of an absurd claim because that's a lot of unnecessary computation. What we want is a way to solve this for a formula. So let's solve. An is equal to, okay, well the first number we want is 3. So we want a of 0 to equal 3. So what's a good way of doing that? Well, we could take our number 3 and, okay, we have 3, but this needs to be multiplied by something. So a1 is going to be 6, a2 is going to be 12, so why don't we multiply it by 2 to the n? Okay, so a0 is just 3 times 2 to the 0 is 1. Okay, that's good. A to the 1 is equal to 3 times 2 to the 1. 3 times 2 is 6. Okay, that looks good. A of 2 is 3 times 2 to the 2, so 3 times 4 is equal to 12. Okay, that seems pretty good. So here's how geometric progression solutions work. And these are unique because these are fairly straightforward ways to solve these relationships. These are very nice. If we have a relation an is equal to d times an minus 1, so d is just our constant, and a0 is equal to some number k, then we can summarize this formula as an is equal to k times d to the n. And of course this is going to be for n greater or equal to 0. This section is going to be n greater or equal to 0, and this recurrence relation is going to be n greater or equal to 1. So these are two different ways of looking at things. One is a recurrence relation, the other is a nice formula that allows us to compute any number without needing to know the previous numbers. So that's great, but what can happen is we can get some more tricky examples. So for instance, this sequence 0, 2, 6, 12, 20, 30, 42, I hope you can see the pattern just by looking at it. To get from the first to the second, we add 2. To get from the second to the third, we get plus 4, then plus 6, then plus 8, plus 12, plus 10, so on and so forth. So another way of writing this, and I know this technique is going to seem like I'm just pulling it out of my butt, but it's hard to see, and the fact that somebody else has shown me how to do this makes it a lot easier. So would I expect you to just understand what I'm doing straight away, or how I got to this solution? No. That's why you're watching a video, so you can see someone else do it, and hopefully you get some insight into future questions or future examples where you see something very similar. Okay, so let's write this as a1 minus a0. So this is 2 minus 0, this is equal to 2. Okay, a2 minus a1 is 6 minus 2, which is 4. Again, what I'm going to do is just to make things super clear, I'm going to write this as a0, a1, a2, a3, a4, so on. Okay, a3 minus a2 is 12 minus 6, which is 6. So we can see this pattern here. So following this pattern, we can see that an minus an minus 1 is going to be 2 times n. Okay, so what we're going to do now is we're going to add all of these up. So let's add up all of these formulas, and what we're going to get is, well, okay, a1 minus a0. Let's add up the left side first. a1 minus a0 plus a2 minus a1. We're going to get a1 minus a1. So these a1s are going to cancel. Then we're going to get a2 plus a3 minus a2. Okay, so these a2s are going to cancel. And similarly, the a3s will cancel. All the way up for the an minus 1s will cancel. And we'll be left with an minus a0. And this is going to be equal to 2 plus 4 plus 6 plus 8 all the way up to plus 2n, which we can just factor out a 2, and then we get 1 plus 2 plus all the way up to plus n, which we can write as 2 times the sum from I goes to 1 to n of I. And if you remember this formula from a calculus course, I don't expect you to know the formula for any exam or test questions that I have on my website. If I did, I would give you the formula. So whether you need to know this formula or not depends on your professor. But this is the same thing as 2 times n plus 1 over 2. So this simplifies to n times n plus 1. So the recurrence relation solution is an minus a0 is equal to n times n plus 1. What is a0? Okay, let's take a look here. a0, 0. Okay, so an is equal to n times n plus 1. So this is the solution. So that might have been a little bit fast, and it's going to be fast because, well, this is a unique way of looking at recurrence relations that you probably haven't seen before, adding up a bunch of equations and summarizing. So instead, well, first we should check to make sure it works. Let's pick a6. So a6 we know is equal to 42. That's this number here. So A6 is going to be 6 times 6 plus 1, which is 6 times 7, which is 42. So it works. Very cool. Okay, here's a nice way of looking at things. When we have any recurrence relation that looks like an minus 1 is equal to some number, okay? What we can do is say that, well, we should probably define a0 to be some number c, and this is for n greater or equal to 1. If we ever have any relation of this form, this is, okay, there we go. This is equal to, so an is going to be equal to a0 plus the sum as I goes from 1 to n of k. So, in our previous example, we had an minus, well, let's do this in a different color. We have an minus 1 is equal to 2 times n. We had a0 is equal to 0 for n greater than or equal to 1. This an is equal to a0, which is 0, plus the sum as I goes from 1 to n of 2 to the n. We can simplify this and say this is 2 times the sum of I equals 1 to n of n. We just factor out the 2, and this is equal to 2 times n plus 1 all over 2, which we know cancels, and we get n times n plus 1. So this is another little formula for recurrence relations that is pretty important. This should be a little bit higher. This requires an minus 1. If you have a number here like 3, it does not work. We will cover that next time, but for now, there's your solution. That might have been tricky, so I definitely suggest going over this very slowly. In fact, for those of you who are still saying, where the hell did that sum proof come from? Oh, e of I equals 1 to n of I is equal to n times n plus 1 over 2. You should know this. Why does this work? Okay, here's a proof of why this works. Let's do this impromptu proof. We're going to take s. This is going to be equal to 1 plus 2 plus 3 plus 4 all the way up to n. We're going to take the same sequence, except we're going to take it backwards. So this is n plus n minus 1 plus n minus 2 all the way up to plus 1. Okay, let's add these together. Let's add this whole sequence together. So 2s is equal to, okay, well 1 plus n is n plus 1. N minus 1 plus 2 is n plus 1. N minus 2 plus 3 is going to be n plus 1. So this is going to add up to the last number here, which is n plus 1, which is n plus 1. Again, I'm just adding vertically here. Okay, so how many numbers are there? Well, there are n numbers, so this is added n times. So really, 2s is equal to n times n plus 1. So that means that s is equal to n times n plus 1 over 2. So this is equal to the sum of I equals 1 to n of I, and that's n times n plus 1 over 2. There you go. That is the proof of the sum. For those of you wondering where that came from, if you ever needed this, I would provide it. Your prof might not. So that was some very simple recurrence relations. I say simple not because they should be easy to you, because they shouldn't be if you're just seeing this for the first time, but simple because the next videos are going to be much, much harder. So If you have any questions, leave them in the comments below or leave them at the subreddit at reddit.com/r/trevtutor, or you can go to the website or email me directly. If this helped you, feel free to share it with your friends, because it will probably help them too, unless there is a curve in the course, in which case do not show them this information at all, because your grade will probably suffer because they will do good as well. Unless you're a kind person. So, hopefully you are. I'll see you guys next time for some homogeneous recurrence relations.